In today's video, we want to discuss complex numbers, but we want to discuss them with reference to the question that I've got there on the board. It is not a question from a past examination paper, as is the case in previous videos, but it's just a question that I pulled out of a textbook because I wanted to highlight two important aspects of a complex number, which is the polar form of a complex number and the exponential form of a complex number. The form in which z is written there is the standard form. So we want to be able to change from this to that to that. But before we do that, we need to calculate two quantities associated with z. Now, let's first of all represent our z in what is called an Argand diagram. In an Argand diagram, the horizontal axis is called the real axis. So this becomes the real axis. It's exactly like your XY plane, except that this is now the real axis and the vertical axis is the imaginary axis. Okay, so we are going to represent z on this diagram, which is called an Argand diagram. An Argand diagram. So we want to represent z on an Argand diagram. And now, so for our z, the real part is this. And the imaginary part is equal to 8. So if we are going to plot z, we must go 15 along the real part and 8 along the imaginary part. So supposing this is 15 going this way and our 8 going that way. So our complex number z would be represented by that point there, just as in the case of vectors in the xy plane. And if we join this point to the origin here, the origin O, then we have a line whose length is r. The length of r is called the modulus of z. So it's denoted by z like that, and it's equal to, is called the modulus of z. Okay, obviously from our elementary coordinate geometry, we know that r, which is the length of this line, is actually equal to this squared plus that squared, okay, from elementary geometry. Okay, so then we can also talk about the argument of z. Supposing the angle that this line makes with the positive x-axis is equal to theta, then the angle theta is called the argument of z. So it's called the argument of z, and it's written as arg z. Well, what is theta in this case? Theta is equal to arctan this over that. Okay, so which is equal to, in this particular example, theta or arc z is equal to arc tan 8 over 15. Okay, so, but before we go on to calculating this, let's work in general terms. Let us work in general terms and suppose that in fact this is our z is a complex number, which is, supposing our z is equal to x plus I, y. So that this point here is the point x, y. Okay, so its modulus is r, its argument is theta, and it's represented by the point xy. So we can define our modulus, so we can say our z, modulus of z is equal to the root of x squared plus y squared. Okay, this should ring a bell because that's what happens in coordinate geometry. Secondly, our argument of z, which is argz, which we said is theta there, is equal to arctan y over x. Okay, so for any complex number represented on the argand diagram by the point xy, the modulus is root of x squared plus y squared. The argument is arctan y over x. Now we can come back to our z now that we've got the formulas. Let's put them up here. Yeah. Let's just put it up here and say our theta. Remember, theta is argz is equal to arc tan y over x, and our r here, which is equal to modulus of z, is equal to the root of x squared plus y squared. Okay, so we can get rid of these guys. And surely we don't need all these guys. All right, so what do we do now? So what is our x? Our x is 15. What is our y? Our y is 8. So therefore, r, which is our modulus of z, is equal to the root of 15 squared, which is 225. I hope I'm right. And the square of 8 is 64. All this under the square root sign. Let's quickly punch in the numbers. So it's 225. Oh, I put too much there. 225 plus 64. That gives me 289. 289, square root of 289. That gives me 17. So I'm getting here modulus of z is equal to 17. Okay. What about the argument of z? Argz, which we said was arctan y over x, which in this case is 8 divided by 15. We should be getting something there. So we get our 8 divided by 15, which is that shift arctan, which is at 0.49, which is equal to 0.49. My angle is in radians, 0.49 radians. So let's summarize very quickly what we achieved so far. We have discovered that if this represents our complex number and r represents the line, the length of the line from 0 up to the point that represents our complex number, r is the modulus of z, the complex number. And the angle here, which the line here makes with the positive x-axis, is called the argument of z, and is given by argz, or theta, is equal to arctan y over x. And argz, of course, is given by the distance formula as simply square root of x squared plus y squared. So far, so good. Now, let's go to the polar form now. The polar form, we need to move from this form, the standard form, to the polar form. Do we need to get rid of some guys? Yep. I think we need to, let's just collect our values here. I'll put them somewhere down here. So it's going to be our z is equal to 17. That's what we found. Our arg z, we found 0.49 radians. So there's a nice little box there for the 2. So we can get rid of this stuff here. Okay. We can get rid of all this here. We need our nice little diagram. So now, there is our complex number now, again, represented by the point xy, and it's of length r, which is its magnitude, and theta is the argument of z. Now, when we look at this triangle here, I have dropped a perpendicular down here from the point to to the x-axis there. So if you look here, this distance here, which is y, which is equal to y, of course, is actually equal to r sine of theta. So y, you can write here, our y is equal to r sine of theta. This distance here from there to there is equal to x, but from our right angle triangle, it's equal to r cos of theta. So we can have x is equal to r cos of theta. Remember, our complex number z is equal to x plus iy, where, of course, this is the imaginary part and this is the real part, just as it is in this case. Our 15 is the real part and our 8 is the imaginary part. So instead of our x there, we can write r cos of theta, and instead of our y, we can write our y cos of theta. So our z now becomes x, which is r cos of theta, plus I multiplied by r sine of theta. Remember, I multiplies y. So we can take out our r there, and we have r brackets cos of theta plus I sine of theta. This is the polar form of the complex number. So we can write it here. This is the polar form. This is our polar form of the complex number. Okay, so, I just repeated what is already there. But anyway, so now that's our polar form of the complex number. Now we want to get to the exponential form. As for the exponential form, I'll just give it to you. You can go to your textbooks and find out the derivation. It's not complicated, but just a little bit involved. The exponential form of a complex number is z is equal to r e to the power I theta, where again your theta is the argument, your r is the modulus of the complex number. Now in terms of our z there, first of all, let's see how we can write it as in polar form. So in polar form, we have calculated our r, which is 17. Our theta is that. So z in polar form, perhaps let's write it in red. Z in polar form will be equal to 17, which is our r here, brackets, cos of 0.49 plus I sine of, these two guys are getting in the way, so let me just get rid of them, because I'm really writing it in a crooked way. So it becomes I sine of 0.49. Of course, everything is in, we should put square brackets here. How does it do? Okay, there we are. So I'm putting my square brackets there. So, okay, there is your complex number in polar form. This particular complex number z, when it's written in polar form, this is the argument of z, this is the modulus of z. What about in exponential form? Again, we've got our r, which is the modulus of z, and we've got our theta, which is the argument of z. So z in exponential form is equal to 17 e to the power 0.49 I. Of course, the theta is in radians, as it is in this case. All the time, my theta is in radians. So those are the three forms of a complex number. The first one is the standard form, then comes the polar form, and then comes the exponential form. In our next video, as I said at the beginning, this was not taken from a past examination question, But there is a question from paper 3 of 2022, if my memory serves me right. I'm going to pull it out, and that's what we are going to deal with in our next video. No, not the next video, but the one that comes after this one. We're going to deal with a question that covers all the aspects that we covered today. It contains all the concepts that we dealt with this day. I wanted to say morning because here it's morning. I'm not sure what the time is where you are. But when we see you again, till we see you again, bye-bye. And thank you very much.